Now I want to switch gears and talk about present the history of accelerators. So it's a good place now that we we started the course talking about particles, how they interact, and then moved on to momentum, how to actually do a calculation where two particles are hitting, and then if you did the homework, that showed you the angles and stuff. So now it's like a good place to pause and talk about how do we even accelerate? How do we get these high energy particles in the first place? And there'll be a follow-up presentation later on detectors. Okay, so this is just to accelerate, and then because then you need detectors to actually see them, but we won't talk about them until later. Okay, so the first kind of you can say with an accelerator would be a cathode ray tube. Everybody know this cathode ray tube? Okay, in the old days, TVs were made of cathode ray tubes. It's basically a big giant light bulb to evacuate the air, and then you have an electrode that goes through the glass, and it's put on a high voltage and sometimes heated first, but electrons are emitted and then accelerated. This evacuated tube. You need evacuated tube because otherwise you'll hit the atoms. But anyway, the J.J. Thomson was the person who either invented it or perfected it, and he put up the kilovolts on the limbic. So in terms of being an accelerator, this would be a 2 kilo electron volt beam. He used it to discover the electron in 1899, and subsequently did a bunch of experiments, deflection experiments. Also put it in a magnetic field so that they move in a circle. So this was we discovered the electron. So by 1927, that's the extent of how much we can accelerate large particles. Rutherford issued a challenge in 1927. He said what we require is an apparatus to give us a potential on the order of 10 million volts, which we can be safely accommodated in a reasonably sized room and operated by 3 kilowatts of power. We require an exhausted tube capable of withstanding this voltage. I see no reason why technical requirement cannot be that. So why 10 million electron volts? Well, we know the alpha particle, a proton is like at 900 mega electron volts, and the alpha, kind of the kinetic energy of alpha particles on this order. So something like greater than that, because we want to have more energy particles and not use a static radioactive source. And the challenge was defeated by what was invented later called the Van de Graaff accelerator. You're all very familiar with this. It's actually invented down the street in Princeton by Van de Graaff in 1931. Oops. And in 1929, so he built this using very, very rudimentary, a tin can. He bought like the silk ribbon to rub things at a 5 and dime store, and he would showed his the dean, the department head, about with the head of the physics department. He showed them, and he wanted to make an improved version, and he asked for $100 to make an improved version, and he had some difficulty getting $100, but eventually did it, and he got a bigger one that was this is the bigger one, 1.5 MeV electrons, and you all know the principle of this, right? basically you have a nowadays a rubber belt, but when you were rubbing that rod, this is just doing that rubbing mechanically. So the rod, the belt gets deposits charge onto the cylinder here, which then gets distributed in the electric sphere. This is the one he eventually built a much bigger one at MIT. This is go up to 5 to 10 million electron volts. The problem was they built it in this open hangar, and a lot of pigeons would nest up here in the rafters, depositing a lot of their droppings, and this would lead to a lot of sparking into the arc. So once it sparks, the voltage is going down. But this would be called state-of-the-art accelerators at this time. In 1932, Cochrane and Walton built what's called the Cochrane and Walton accelerator. These are Cochrane and Walton are the two gentlemen on the side, and in the middle is Rutherford. And the accelerator is basically their version uses an AC circuit to resonantly kind of deposit charge. So these are diodes, and when the charge is positive, current is pushed onto one side, and when it goes negative, it can't go back. This side would be negative, so then it'll be accelerated from capacitor C2 and pushed to this side, and then it can't go back. And then the voltage switches to positive up here, and then they're accelerated back up through the diode and can't go back. So eventually, basically, these are stepwise accelerations, so you can get higher and higher energetic. Once they get to V0, they're pretty high energy, high voltage, and they leave the electrode with high energy. So this is a kind of a prototype at this time. We're talking about a few hundred keV. Here's one built and safe. You can see the operator is inside this box. Shielding. This is about 400 keVs of protons. You get to a room of size. Accelerator. These are the diode bridges. So all the way to the final electrode. 1.2 MeV, and nowadays it's used as an injector in the big accelerator. So this is, you have many stages. So this is the primary stages to accelerate to 750 before they're sent somewhere else for further acceleration. Okay. Now we talk about the linear accelerator. So the same kind of principle, you kind of do kind of a synchronous acceleration or resonant acceleration. And the idea is illustrated well with this graphic. You have a particle coming in, and you have an AC voltage. So it's alternating. So initially it's attracted and repelled from here, and then attracted and repelled because it's the voltage switches. Now, can anybody guess why the tubes are different lengths? Yeah, the part is accelerating. And
so the same, keep the longer amount of distance.
Yeah, that's right. And you also, it's also relativity too. You have to do it you have to adjust for that too. At some point, they will actually see shorter tubes. Yeah. So instead of fixing the timing, you instead of changing the frequency to change the timing, you actually change the length. to get the time. Okay, so first demonstrated in 1928 was 50 kV kilovolt potassium ions. Here's another graphic of accelerator. Same idea. So think of it as riding a wave, right? Surfing a wave. The wavelength changes. Frequency stays the same. The wavelength changes as it moves, as it accelerates. So here's a very famous linear accelerator, the Stanford Linear Accelerator. In California, you have accelerating electrons and positrons to 100 GeV. They're both produced in here and then sent through some like booster. There's a positron source and sent through this sort of like these beams, split them so that then they can collide with each other. There. And this is just a picture of what's happening with electron and positron. They're being made at different places and set to the main drive. This is an aerial view of the Stanford Linear Accelerator. This is Highway 101. It goes underneath a freeway. I've been here one time, but not to do particle physics, which is atomic physics here. But it's kind of, this is just, it's not underground, it's above ground, but it's a tunnel. So remember that this all has to be evacuated. Along the whole line. This is about a kilometer. So linear accelerators have been used in medicine. There's a picture of a baby, I think, to get rid of tumors, or 25 MeV in energy. They've been used in industry. Not really sure what what, but I guess some kind of something to do with powder coating is metal. I'm not sure. And now we go from a linear accelerator to a cyclotron, and that was invented by Ernest Lawrence at Berkeley. This is the building, radiation laboratory. Just a few hundred feet from where I the building where I and the principle, we kind of showed you this slide before. The principle is now you have the accelerating electron plus minus and the electrons or charged particles created, and they accelerate towards the positive. Once they get in, the voltage is flipped. They move back out. And the thing is, the cool thing is all inside a magnetic field, so they're gonna automatically go around in a circle just because they're charged particle magnetic field. You don't have to and make a tunnel on it. And it's automatically synchronized because if you look at the equations, remember F equals QV plus V, the force due to the magnetic field is always perpendicular to the velocity vector. So it'll execute a uniform circular motion, right? Execute uniform circular motion, and then you can work out the radius. So the radius here depends on the mass, the speed, the charge, and the magnetic field. The stronger the magnetic field, the smaller the radius. The faster the speed, the bigger the radius. Now, the speed we know goes as 2 pi r over t, the circumference divided by the period. And see here that's cool because the 2 r can cancel. And if you just solve for the period, you get this. It's something that doesn't depend on the speed at all. It just depends on constants, the mass to charge ratio, and the magnetic field. So what does that mean? That means this frequency can be, you don't have to change it. You know, accelerate particles, slow moving particles, as well as fast moving ones. So they just spiral out until you eject it. So that's the beauty of the cyclotron. Not do anything in terms of timing. So just time themselves. The first cyclotron was 5 inches, just basically the palm of your hand. It was built in 1932, gave you 1.2 MeV already. Here's the lab where they built that. I think one of these magnets ended up but this is what it looked like. So the experiment will be all it happening inside the magnetic field. The magnetic field is assumed to be uniform. So the more uniform the magnetic field, the better. And so if you wanted, you saw in the picture, it got faster and faster. So if you wanted to go even faster, you had to have a bigger magnetic field in space, right? No, I don't mean bigger strength, but as larger in space. It has to occupy more constant magnetic field over a larger volume. And so we get down to the 60-inch cyclotron. Here it is. By this time, Lawrence had moved his lab up to what's called the hill, the slope of Berkeley, where the lab is going to be built, and that's the Berkeley laboratories. And then you get even bigger, the 184-inch cyclotron. By the time I was here at Berkeley, they were decommissioning this building and just cleaning it up. But this is 184 inches. It's just right here, just the tip of the pole magnet. And then this is the largest cyclotron, the world's largest. Yeah. Doesn't say how big this is. Well, you can see it's pretty big. There's a man standing.
600 trillion versus.
Oh, okay, sorry. I thought that was the energy. Yeah, 620 inches. See the person there? These are these little coils are called shim magnets, so they're trying to fix the fields so that it's perfectly perpendicular and not have any not bending and stuff. So 520 MeV. The next type of accelerator would be called the synchrotron. Now, obviously, we can't make them bigger. These magnets, at some point, that's just too cost prohibitive and material wise as well to make a big magnet. So we're just gonna do a bunch of linear accelerators, but bend them in a ring. So in this way, you can still have this idea of keep them going around, getting them faster and faster in energy, but you do it at small linear bits at a time. Okay, so the synchrotron, so you can think of it as combining the synchrotron and the linear accelerator and the cyclotron together, right? The magnetic field only occurring at some parts of the beam line, not the whole thing, so that we can bend it. The energy here, 100 GeV. It's a nice graphic. Now, synchrotrons are also very useful to do auxiliary experiments. A lot of labs do that. So you can split off the main beam to people's experiments, all located all around, right? So people are doing experiments, sometimes not even having to do with physics, chemistry, material science. You just want a beam to with a source of high energy charged particles. And the synchrotron, of course, is a part of the next thing in this part of what's called a collider. Now, we said that moving from a fixed target to a center of mass frame, you get many advantages. You get higher energy. And so a collider is basically two synchrotrons together, and then kind of time it all such that they collide. Now, none of these beams are continuous. They're just bunches, right? Once you can make a bunch, you accelerate that one bunch only, and then you time it so that they collide at the right time, at the right place. Basically at the center of your detector. So the tevatron, 2 eTeV, 2 TeV, that's 2,000 electron volts. at Fermilab. It's accelerating protons and antiprotons in a counterpropagating way. And this is how the top quark was discovered. And of course, CERN is a collider. This is a LHC. These names, Atlas and Alice are the name of the detectors. Now at CERN, there's also the precursor was the Large Electron Positron Collider, or LEP. It's a tunnel, an underground tunnel, accelerating electrons and positons. In 1989 to 2000, it had 209 and a large hadron collider. Basically, they use the LEP as a booster ring. Like they just fill a hadron collider. And it's still operating today. It's where the Higgs boson was discovered in 2012 at 12. It's a picture of the LHC tunnel. And this is what it looks like. Those see counterpropagating bunches. Here's a slide through those two bunches sitting on the detector. And like I said before, we'll have a presentation on the detector. But that's the second technological hurdle to detect. As particles are getting higher and higher energy, you have to have different kinds of detection. This is the an idea of what the next generation would be. So if you look up here, this is the LHC. So now we're talking about much bigger, 3-4 times bigger in diameter, 100 kilometers in circumference, I think. It's called the Future Circular Collider. It would have a circumference of 90 to 100 kilometers and reach an energy of 100 TeV. In terms of comparison, the LHC is only 27 and the Tevatron is only 6. So the idea here is to go beyond, and it's not really clear what we already found the Higgs boson. So what should be discovered would be if we discover anything, it'll be something beyond the standard model. So that's great, but it's not going to verify any theory now, at least for in terms of physics beyond our theories beyond the standard model, like supersymmetry and things like that. It's not clear, and those things are off. So we might, it very, very well, if you reach this energy, you don't see anything. So that's even higher, but who knows? This is a graphic of accelerated energy as a function of time. So pretty much follow the linear, a lot of log scale. So log scale, power log scale. Collider has us there. So there's, you can see it kind of tailing off, like a synchrotron technology kind of bends down, not following the line. And Collider may be doing that as well. So we might very much need new technology to keep on this curve.